Yes.
Thank you for the invitation. I would say a little bit about what we are doing about digital twin modeling in the energy system. And I'm going to talk about 3 different cases we are working on, but first I want to start with saying a bit about what a digital twin is, at least from our perspective. I mean, there's many perspectives today what actually is a digital twin, but we go along with saying that it's a digital representation of a physical system. It might be a single asset like a pump, or it might also be a whole system. So we have been looking a little bit into definitions in the past on digital twins, and there's a very commonly known definition from NASA back from 2013 that is very focused on actually like modeling the physical properties of a system. But we have been working also a bit with our own definition, because we have a software perspective on building these digital twins. So we actually came up with an alternative definition here some time ago, or earlier this year, that we say a digital twin is a composite of software artifacts linked to a specific cyber-physical system, basically a physical twin with a specific goal of improving real-time insights, decision-making, or operations. The reason why we're focusing on this real-time insights and decision-making is because many of the projects we have been doing in the last years is very much focusing on other decision-making or improving the operation of the system, typically through set point optimization. So the twins we have been working with have been looking on these purposes, monitoring and prediction, optimization, control, and lately also on simulation. The early versions we did of twins was very much focusing on monitoring and optimization control, and the later you will see in this presentation is very much on simulation and prediction. So we have also been going through the literature lately in order just to see, you know, where our work fits in a bigger perspective. And since we work with energy, of course, we were very interested to see how much was actually done in the energy sector. And I have to say, to our surprise, we found very little published work actually on digital twins in the energy sector compared with other areas. Of course, it's not a surprise that there's a lot of work in manufacturing and production, and also quite a lot in aviation and buildings, but it's underrepresented actually in the energy sector. But of course, it's just nice because then there's more stuff to do there. So when each time I'm trying to explain what we are doing, I'm also trying to make a picture, a rich picture, trying to explain what our digital twins looks like, such that I'm not just going to present like a UML software model. So I've tried to come up with this picture you see here, where actually where I try to picture the elements of the twin, basically the historical state that we capture from the physical twin, and also the representation and visualization of the current state of the twin, and then basically the purpose for which we built the twin, actually be able to do some prediction of the near future or the state of the twin in order to optimize some aspect or make some prediction that might, for instance, be used for predictive maintenance. So what we basically take in here is sensor input or input from a SCADA system that goes in to represent the state, the current state of the twin. That is also used for the starting point of the prediction, where we typically use things like weather forecast and electricity prices, such that we can try to optimize set points. So as it's shown here, you know, we use it for decision support, because it's our experience in most cases that people don't like actually control. They prefer to be in control. So therefore, most of the things we do is actually generating recommendations that can help people to try to make changes to the operational schedule in order to improve some aspects of their production. Of course, if you can generate the recommendations, it's also relatively easy to turn over to active control, and that we have also been doing in some cases, but it have typically been on smaller production systems that have been built for test and not on actual production system when it comes to active control. That we don't only do recommendations. So I'm going to talk about 3 examples today. The first one is the research we do in smart buildings. And the building you see here on the screen is one of our buildings on campus that we actually use as a living lab. It's a 9,000 square meter building. It's built to the newest building standard in Europe. It's a low energy class. And it's highly instrumented with meters and sensors that basically allow us to monitor all energy consumption in the building, and it also allows us to monitor the whole indoor climate. And in addition to that, we also have occupant sensing, such that we know how many occupants enter the building and how many occupants exit the building. So, so it gives us a very good way of correlating energy use with building use in order to try to make some better optimization. So in a past project, we actually built a virtual simulator of the building that we could use for the prediction. And we also used that simulator to do some model predictive control on the building in order to see if we could make an optimized energy control of the building compared with the current building management system that are installed that are rule-based. So what we do here is we can run the same software on the virtual building as we will actually later run on the physical building in order to optimize it. So we run some experiments and compared our model predictive control that here is based on genetic algorithm, a multi-objective generic algorithm that optimize different perspectives. And we could see that we could save around 25% of the energy in this way. And we could also drastically reduce the number of comfort violations compared to rule-based control. Yeah. One of the other things we're working at the moment is a production system in horticulture, where we actually look into how we can optimize the whole production and the energy system of modern greenhouses. So here we are working with 3 different twins. We're actually doing a twin of the energy system in the commercial greenhouse, and that's because a lot of the commercial greenhouses actually have their own little energy system with a combined heat and power plant where they can both produce heat for heating up the greenhouse compartments and also generating electricity for the artificial light, or they can also choose to buy it. So it depends actually whether it's cheaper for them to produce their own electricity compared to buying from the electricity grid. Then we make a twin of the greenhouse compartments themselves. That's actually the grow environment. And we also do a twin of the whole production flow through the greenhouse, such that we can do some co-optimization between the production flow and the greenhouse climate compartments. But this is the objectives here we are working with is actually we try to optimize the use of the artificial light depending on the weather forecast, such that we eliminate all unnecessary use of artificial light if we will get enough natural light over the next 72 hours. And that we optimize up against the electricity cost for 72 hours, such that we get the cheapest price for the use of the electricity for artificial light that we actually need to use. And some of the results we have here shows also that we can make a 26% optimization with respect to the cost of using artificial light. And this system today we have running in a few of the major Danish growers that use it for optimizing their use of artificial light during the spring and the fall season, where we have a lot of change in the natural light condition. During winter, there's not so much use for it because you need to use artificial light all the time. And during summer, there's no need for artificial light at all. So it's spring and fall that are the interesting periods here. Yes, and actually what this allows the growers to do also is to see when they are producing or when they are buying based on their own needs. So this allows them actually to run the whole energy system like a small virtual power plant, where they, based on the needs of the individual compartments, can optimize their own energy production compared to the grid from buying and selling electricity. So that's also being used to some extent at the moment. The last example we have are the work we are doing on smart grid, or more precisely on flexible energy use. The example here is for charging of EVs, but it's basically relates to all flexible energy use that we will see in the coming years, and what are the implications for grid stability. What we are doing is we make a digital twin of the distribution grid in a neighborhood. That means we make a digital twin of the low voltage part of the distribution grid, meaning that we are working with typically something between 100 and 200 households under the low voltage transformer. And here we want to investigate the differences between doing smart charging and simple charging. Because it's have been stated that if you use smart charging, you would be able to leverage the peaks of the electricity consumption, and also to use basically electricity when it's considered to be cheaper. Well, this is a good idea or a bad idea. Well, we'll see that later on. So we have built here a digital twin layer where we're modeling the capacity of the distribution grid. We're modeling the EV charging boxes, and we're also modeling the heat pumps in the individual households, and run it up against the algorithms that have been proposed for basically do charging of EVs. So what we have implemented here are basically strategies from the literature, but also some of the strategies that are actually being used by the EV charging suppliers today. So what we have as input for these charging strategies is basically just the price signals, such that basically because most of these charging strategies try to use the electricity for charging the EVs when the price is low. So that is what we try. So in order to have a baseline, we have done experiment with simple charging, and by simple charging we mean that's the charging that happens when people just come home from work, they plug in their EVs, and then the EV starts to charge until it's fully charged. And what we've done here is we try to say, okay, what is the expected growth or the adoption rate of EVs over the coming years? And then how will that influence the grid stability when all of these adopted EV will start to charge? And based on this, we saw that we will have our first capacity problem in a typical Danish distribution grid in 2031. When people just charge, in this traditional fashion by just plugging in when they come home. So now it's really interesting to see what happens if we start to apply these smart algorithms for smart charging. And this is also what is going to happen on our grid whenever we are trying to apply some other software for actually having increased flexibility for any device on the demand side. So you could think about this not only for EVs, but also for smart operation of refrigeration systems or cooling systems in grocery shops and so on. Good. So let's have a look at this is just the result, that how many EVs was being charging and what is the overload. But if we look at the results of it, is that we have 11 days with the overload for the simple charging in 2031. If we look at the smart charging, we see that we actually have an overload 1 year before in 2030, and we have a lower number of EVs that are charging at the same time. And that is basically because now we start to actually have some herding behavior, that all the EVs are trying to charge at the same time because the price is low. So the terrible results of this is actually that due to the herding behavior, we end up to have 235 days with overload compared to the 11 days with simple charging. And we are going to have 204 time steps within these 235 days where we actually have overload. So, so if we compare, we can see that with simple charging, we can charge 70 EVs, and we first have overload in 2031 with smart charging, where we are all using electricity when our price signal tells us to do so. We will only have like 45 EVs charging at the same time, and we will already have the overload in 2030. And we will almost have 2/3 of the years we will have overload in the distribution grid, where with simple charging we will only have 11 days with overload. So this basically just shows us that smart charging is not a way of increasing the flexibility in the distribution grid compared to actually just doing the simple charging that we are doing today. So there need to be some other algorithms in place in order to try to create some flexibility, but definitely not price signals. It's not the way to go based on our simulation results. Yes, that was all I had. Any questions?
Thank you both for the introduction to your projects. And Wiebke already has a question.
Yeah, it's actually, I think it's very interesting, all the projects that you showed. But now with the EVs, I was wondering when you predict how the smart charging and the normal charging will behave within the next 10 years. How did you take into consideration that also the demand prediction might actually...
Sorry, I lost that part of the question.
How, I mean, during the prediction of the effect of smart charging in future, how did you take into consideration that also the prediction of the demand will change if we see more and more of these patterns where people try to follow the price? Don't you think that
the way we have implemented this is that we made it as an agent-based simulation? So that means that we use the base load just to simulate what is I mean the real base load that we got for the living lab, the distribution grid in the living lab. So so that just gives the normal household load, and then we made generated load profiles for people's charging of the EVs based on data from Danish statistics on how far people drives to work, and then we made a distribution of that such that we get a representative use of EVs based on the data for people's driving behavior. So we have simulate people driving behavior, and then of course we have then increased it as we have an increased adoption rate of EVs into the future.
But
so
keep
that
the price
actually
signal the same.
We run the agent-based simulation for simulating these. Basically, we simulated until the year where we had the first overload, and then we simulated that year to the end. So it is an agent-based simulation that have been running for basically from a 10 years period, or simulating 10 years. And so it's and we just used I mean price data from Nord Pool Spot that we have then repeated.
Yes.
Also to have. So of course,
I think that's well, maybe where my question is.
Yeah.
Like,
so actually, you know, to what extent we will see increased fluctuation in electricity price, or whether we will see flat electricity price that we more or less saw for the last half a year due to the war in Ukraine is of course, I mean, there's an uncertainty is actually, you know, how much fluctuation there will be electricity price, and then how deep the valleys will be. Because the deeper the valleys, or the, you know, the periods with a very low electricity price, of course, then that would give more hoarding behavior if you have algorithms that strictly goes for the lowest electricity price.
Yeah.
But it's just difficult to implement other, or at least in Denmark, it's difficult to implement other algorithms since we got full flex in 2020. That actually provide spot market settlement for all electricity consumers. So you cannot really tell somebody to charge at a more expensive time period, because, you know, that's not fair. I mean, everybody wants electricity when it's cheapest, and that's also what basically brings the distribution grid down. So it's a perfect storm.
But wouldn't there be some game theoretic aspect? Like the electricity price would never go that low because the electricity supplier would know that the consumption would rise too far.
Well, the price is settled 24 hours ahead.
Mm.
So there's no game theory in it, because you already know when the electricity is cheap, because that is the way Nord Pool Spot functions, you know. I mean, this afternoon at 1 o'clock, I know what the electricity price is going to be from midnight to, and then for the next 24 hours. So we don't have any real-time pricing. It's all a spot market settlement.
I understand.
So when we put when we add the heat pumps on top of this with the same kind of smartness, then we get a true disaster.
But I think the prediction of the demand also gets more intelligent, right?
Yeah, but it doesn't change anything. I mean, you might predict the demand, but it doesn't help you, because you have no way of influencing the end consumer in the current system.
Can I ask a quick question? I think I missed a small part of your presentation. You talked about multi-objective optimization. I kind of missed after that how you applied that, but I'm sure you mentioned it. Now, my question is that it's an agent-based simulation. So did you take any action on the simulation, or you just went down the path of prediction that this is what's going to happen? For example, is there any optimizer comes back and mentions that if you change things in this way, or you change the price profile in this way, then things will be different and the outcome will be different?
No, what we do here, we just simulate the existing conditions. I mean, we take the framework conditions as they are given, the regulation as they're given, and the tariff models as they're given. And then we just show what is going to happen if we keep the current regulation. And we just go forward by adopting electrical vehicles and heat pumps.
I see. Okay.
So if we, you know, right now there's not a huge problem in the next few years, but if we don't do anything and we continue the adoption of EVs and heat pumps, then we will have a distribution grids that basically stop working.
Right. Okay. Do you have any recommendation for actually taking actions on it?
Well, we are just in the business of showing how terrible it's gonna go, because so many people are making all kind of suggestions of solutions. And what we do is we take all these suggestions and just shows that they're not solutions.
Yeah, no, what I meant was that not that what the recommendation to the governments or to system is, more like how would you interfere mathematically with the system to come up with the recommendation? If someday someone came and said, look, I'd like you to tell me what would be a good action. Now that we know the outcome is terrible, how to fix the problem. How would you actually go about this problem? How would you actually apply methodologies? Like, do you apply fuzzy logic or something to see different actions would result in different outcomes and then end up with a recommendation? I'm not saying that recommendation could be good or bad. I mean, how would you even come up with something like that?
For the time, we have not focusing on trying to come up with a solution for solving the problem. We have for the work we do on the distribution grid, we're focusing on actually evaluating what had been suggested, right. And also provide a platform that can be used by regulatory authorities to see what are the consequences of what they suggest before it's actually being implemented. We have our latest tariff model that was put in place this year, 3.0, that actually gives, I think it's four tariff period from that depends on the season, and it's just it basically just makes the problem worse because it's put a higher tariff on the so-called boilerplate hours and a lower tariff on what used to be the low price hours. It just basically means that even more people would be pushed into these low price valleys if they have any software that can respond to the tariff and to the spot market price. So it just actually the new tariff model actually just make the situation even worse compared to the old one that was just a flat tariff, because at least that was neutral.
Right. Thanks very much. Very interesting, informative.
Yep.
I have a short question from my side. I'm investigating a similar topic with charging of electric vehicles. And have you heard about?
Is it just me who have trouble with the sound? Because I lost the second half of your question.
Okay, sorry. I will repeat it, or I haven't started. Have you already had experience with some logic in the local grid, in the 400-volt grid, of a decentralized logic in the grid and having their energy storage systems? Have you been investigated something like that? So because there are approaches going away from having a centralized provider, which is controlling all the consumers, down to a decentralized solution. I think this is where the way goes. This is what I currently see.
Yeah,
maybe. Yeah.
I mean, the thing at the moment is that there's no feedback from the local DSO to the charging suppliers.
Okay.
So there's no way that the DSO can communicate with an aggregator. I mean, it's not in place. So in that way, you know, it's when an aggregator decides to do control on a distribution grid, the DSO have no way at the moment to interfere. So of course that will also just basically give challenges, because if you have an aggregator that decides that now he wants to start a lot of heat pumps because he needs to do down regulation in the market, then you might risk to overload a distribution grid locally if that aggregator operates a lot of heat pumps on that distribution grid and doesn't take it into consideration what is the local capacity on the distribution grid. So some kind of coordination layer seems to be missing.
Yes. This is what I also think. Yeah. A lot of work to do on this in this direction, also in Austria.
Yeah. But I think the challenge that we are facing here, at least in Denmark, is we have a government who publicly say that all of us need to use the electricity when it's cheap, disregarding like what is the problems that follows from it, because the distribution grids have simply not been designed in the 60s and 70s for EVs and heat pumps. They were designed for old-fashioned cooking plates and light bulbs. So many of the distribution grid are actually underdimensioned compared to modern use. And I assume you see the problem in the rest of Europe. I mean, I would be surprised if you don't.
Brian has raised his hand.
Yeah, I just had a question, Bo. I hope you hear me. So now you have shown that how it won't work, but now you also have the model and the digital twin. So could you perhaps use that also to come up with ideas for how it could be solved and showing some opportunities as well?
Yeah, I mean that's some of the next steps. I mean, looking into what could be a solution if you, for instance, consider to make a digital overlay on the distribution grid that allows the DSO to actually provide feedback to the aggregators. But we just need to. Well, there are some challenges in the regulation due to GDPR that the distribution system operator don't know actually who are the aggregator that might aggregate some of the EVs or heat pumps that you have on your grid. So there are some regulatory issues that needs to be solved in order for going for that kind of solutions.
Okay, sure. But the regulation can be changed at least.
Yeah, it just takes time.
Yes.
Just look how many years we had to wait for the change of the regulation of waste heat, right?
Sure.
Yeah.
Thanks.
Welcome.
Maybe circling back a bit to the digital twin topic, Bo, you sort of presented us today with 3 different the kinds of digital twins that were all set up for different applications. And as far as I could see on your slides, they were all set up in different ways. So I was wondering, like, having used that many approaches to digital twins, are there any takeaway points on like what is the best way? What the pros and cons?
They are very much. I mean, the picture I tried to show. I mean, of the architecture of the twin is basically the same. I mean, in all of them, with the historical state and the current state and the predicted future state. That's basically the same for all of them. How we link it up to take in data. The data we take in is typically what we capture and rerun the historical data as the real-time data feed. When we develop the twins for a lot of practical reasons, because it's not easy to take real-time data in from any online production facility for a lot of cybersecurity reasons and so on and so forth. So normally what we do is that we get the data and then we can replay it when we need to simulate real-time data coming in to show the current state of the system. But the architecture is more or less the same. I mean, it is the pattern that is reoccurring.
Thank you for that answer. At some point, would be really interesting to learn a bit more about the models that, like the methods that you used, in a bit more detail. But maybe get another opportunity during this subtask.
Yes.